Hello, my name is David. I'm from the Technical University of Graz, and today I'm going to talk about reinforcement learning, which is one of three major topics of machine learning. It can be seen as an analogy from reinforcement learning in psychology, where we have a human or an animal that takes an action that influences the environment. This change in the environment can then be perceived, and for this perception we feel a reward, which can be positive, then the likelihood of the action is going to increase, or negative, and the likelihood of the action is going to decrease. In machine learning it's very similar, but here we have an agent, which is a computer program or something similar, and not a living human being or animal anymore. Obviously, this computer can feel, so we need to calculate the reward function. Also, we're going to calculate a state, and this can be seen maybe as a classification of the perception of the environment. Usually, reinforcement learning problems are modeled as Markov decision problems, which is a four-tuple containing a set of states called the state space, a set of actions that the agent can take called the action space, the probability function, which is the probability that S apostrophe is going to be the state in the next time step under the assumption that at the current time the state S is the current state and that the action A is chosen. This obviously requires discrete time steps. Then there's also the reward function that describes the expected immediate reward for transitioning from state S to S apostrophe through the action A. So now we have the problem modeled. What are we going to do next? Our goal is to maximize the reward function. But how are we going to do it? We choose the right policy. A policy tells the agent what action to take in which state. It is the cross product from all actions and all states, building to a probability function between 0 and 1. It could also be deterministic, then for every state it is clear what action the agent is supposed to take. And a little more mathematically, here's the function for the policy. It's pretty much the probability that at the action at a specific time point is going to be the action A if the state at that time point is the state S. And this is what we want to learn, what the agent is supposed to learn in order to maximize the reward function. I also want to talk about the state value function really quick, because just updating the policy according to the immediate reward might be a little too greedy, and one way of overcoming this problem is updating the policy via the state value function. We can see it right here. The E just means that it's the expected reward, and then we have a sum over all future time points until the end of the learning phase, and we sum up all the rewards. Then we also see the gamma factor, the discount rate, and it's always smaller than 1, bigger than 0, and it just ensures that future events are taking less into account than the current or than the events in the very near future. Last but not least, I want to talk about the exploration-exploitation dilemma. For that I brought you a real-life example. Maybe I might ask myself, should I study or should I party tonight? Partying would have the higher immediate reward because I just like it more, and this would be exploitation. Maybe there are some options that I never tried before, in this case studying, and just to know how it feels, maybe it has a higher long-term reward, I'm going to try it. That would be exploration. In reinforcement learning, often the epsilon factor is used for solving the dilemma. It ranges between 0 and 1 and is the likelihood that the agent explores, which would mean that a random action is chosen. The factor can either stay equivalent through the entire learning phase or also decrease within time to make sure that at the end, at the learning time, we don't explore that much anymore, but we rather get comfortable with the decisions that we already know have a high reward. Thank you very much for your attention and see you for the next video. Bye bye.